In the last lesson, we talked about the interaction of radiation with matter, and today we will learn how we can detect this radiation. Put simply, radiation detection works by converting the interactions of radiation with matter into an electric signal that we can measure. Different types of radiation require different kinds of detectors. But before we get into that, let's start with the basics. Detection of radiation can be direct by measuring the ionization products such as ionized atoms. An example of direct detectors are the so-called ionization detectors. In some cases, we need to indirectly measure ionization products by converting the ionization products to something that is easy to measure. An example of detectors that make use of indirect measurement are scintillation detectors. I will now explain how both detection approaches work, starting with direct measurements. There are different ways to detect radiation directly. One example is the gas ionization chamber, in which a gas chamber is connected to a voltage to create current, and an electrometer is used to measure this current. When ionizing radiation interacts with the gas chamber, it will create ion pairs, positively charged ions and electrons, which, on the voltage, will create an ion current that can be measured using an electrometer. For indirect measurements, a different setup is implemented. In this particular case, a scintillator material is used. The scintillator's function is to convert ionizing radiation into light photons, indicated by the yellow flash in the figure on the slide. These photons are then transformed into electrons, which are measured by the detector, resulting in an electric pulse. But why are we actually interested in radiation detection? There are three main reasons: to identify a radionuclide or mixture of radionuclides, to determine activity in a sample, or to simply detect radioactivity, for instance, to check if an object or a person has been contaminated. In order to identify a radionuclide, we will need to perform a qualitative analysis. There are different ways to perform such an analysis. We can measure the half-life by performing measurements at different time points and compare it with tabulated data. But this approach doesn't work that well for very short-lived or very long-lived radionuclides. We can also measure the energy of the radiation being emitted, but to perform qualitative analysis using this data, we will need to know what type of radiation with what energy levels a specific nuclide emits. Such information is typically found in a nuclide chart or in databases. For instance, here you can see an example for chromium-51. In the nuclide chart, the half-life, the decay mode, and the energy of the most prominent emitted radiation can be found for most nuclides. As you can see, chromium-51 decays via electron capture and emits gamma photons of 320 kiloelectron volts. Keep in mind that gamma energies in the nuclide chart are given in kiloelectron volts, but alpha and beta energies are in megaelectron volts. Now let us have a look at some spectra and learn which type of radiation is best suited for the identification of radionuclides. In this slide you can see the alpha spectrum of the radionuclide americium-241, which emits alpha particles of 5.5 megaelectron volts. The width of the radiation peaks depends on the detector type and reflects the energy resolution of the detector. Radionuclides emitting alpha particles can in principle be identified by measuring the energy of these particles. However, detectors that can properly measure the energy of alpha particles are uncommon in radiological labs. In this slide you see a general beta spectrum. Since beta particles have a continuous energy spectrum, identification is very difficult. The shape of the spectrum will differ depending on the nuclide in question and could in principle be used for qualitative analysis, but such identification is sensitive to even slight disturbances and is therefore rarely used. A radionuclide is best identified by measuring the gamma rays, if of course the radionuclide emits any. Here you can see an example spectrum of cobalt-60 taken by a scintillation detector. In this spectrum, the most important peaks for identification are the photopeaks, which for cobalt-60 are 1332 and 1173 kiloelectron volts. The photopeaks originate from the photoelectric effect, where a photon transfers all its energy to an electron. What you also see in this spectrum is the so-called Compton continuum, which originates from the Compton effect and results in a sort of continuous background spectrum of radiation. Another feature often observed in spectra is the so-called sun peak. A sun peak appears when two or more photons are detected simultaneously by the detector, producing a peak at their combined energy. The backscatter peak is sometimes observed for high-energy photons. This peak is the result of photons that are scattered back into the detector after interacting with the detector shielding, for instance. Sometimes X-rays as a result of bremsstrahlung can be observed. Bremsstrahlung is created when electrons emitted by the radionuclide interact with the shielding of the detector, which is typically lead. The gamma spectrum of chromium-51, shown on the slide, looks different than that of cobalt-60. There is no sun peak, no X-ray, and a much less pronounced Compton continuum and backscatter peak. On this slide, you can see the gamma spectrum of zinc-65, which is a beta-plus emitter. The emitted positrons interact with electrons, leading to annihilation and the emission of two photons of 511 keV, which produce the photopeak at the corresponding energy level. I hope you now understand that each radionuclide will have a characteristic gamma spectrum. Also keep in mind that the gamma spectra we discussed were made by a scintillation detector. Using other detectors can result in sharper peaks or less background. Now that we've talked about the identification of radionuclides, we will dive into how we can determine the activity of a sample. The activity of a sample can be determined using this formula, in which the count rate measured by the detector, so the number of counts per unit time, is divided by the number of particles emitted and the detector efficiency. The detector efficiency depends on many factors, among which the geometry of the sample. If we know all these factors, we can determine the activity of a sample using radiation detectors. Finally, sometimes we just want to find out if something is radioactive and we are not particularly interested in how radioactive a sample is or what radionuclides it contains. In such cases, radiation detectors are used that can detect low activity levels, such as a Geiger-Müller detector shown here. Before leaving a radiological area, it's important to check for personal contamination. For this purpose, a hand and foot monitor can be used. Thank you for watching this lesson. I hope to see you in Module 2.